So my name is David Harel, and I have the great pleasure of interviewing you, Michael Rabin. We call you Michael, but I will try to stick to Michael. As an interview taking place as a result of you winning the Turing Award in 1976, and ACM are preparing a series of interviews. So maybe you can tell us a little bit about where you were born and how you started to shift into things which are close to mathematics.
So I was born in Germany, in a city called Breslau, which was later on annexed to Poland and is now Wrocław. My father was there at that time, the rector, the head of the Jewish Theological Seminary, a very famous institution in Jewry. In 1935, I was born in 1931. In 1935, my father, who realized where things are going in Germany, took us, his family, and we emigrated to what was then Palestine, now the state of Israel, and we settled in Haifa.
So you were 4 years old.
I was not yet 4, actually. So we settled in Haifa. I have a sister who is 5 years older than I am, and she used to bring home books on various subjects. One of those books was The Microbe Hunters by Paul de Kreef. So I read it when I was about 8 years old, and it captivated my imagination. I decided I want to be a microbiologist.
But your sister became an expert on education.
Yes, later on. But
she is not a scientist.
In the university, she did study biology first, and her expertise in education is about science education, in particular also biology. So I read that book, and these stories about Leeuwenhoek, Pasteur, Sapalzani, the one who realized how bacteria multiply, really captivated my imagination. As I said, I was sure I'm going to become a biologist.
Did you also study Jewish studies at that period?
I studied Jewish studies as well.
Talmud?
Talmud also, but that somehow, even though I come from 10 generations of rabbis, did not really captivate me.
But there wasn't something in the logic there that
No.
later...
In fact, the logic, which is after all different from what we now consider classical and mathematical logic, the logic actually somewhat repelled me, the Talmudic logic.
But there are parallels, Kal vachomer and modus ponens.
Some. But for example, arguing by analogy does not exist in mathematics.
Yes.
And even at that age, I somehow didn't quite accept it. Now, when I was 11 or 12, I was kicked out of class during class time for good behavior. And in the corridor, there were 2 students of the 9th grade who were legitimately out of their class.
So they were about 15.
They were about 15, I was about 11. And they were doing geometry problems. I stood above them and I asked them, "What are you doing?" I haven't heard about geometry at the time. And they were proving, or had to prove, various statements. The one they were looking at was 2 circles exterior to each other. You take a point on one circle and on the other circle, connect them by straight line and you get a segment. The question was, what is the shortest segment connecting these two circles? They didn't know what the answer is, and of course didn't know how to prove it. Now, I looked at it, and all you need to solve that problem is to know the definition of a circle, and also the fact that the shortest between 2 points is the straight line segment between these 2 points. So I immediately saw the solution and explained it to them. Now, the fact that by pure thought you can discover and demonstrate statements about the real world, meaning about circles and their distances, of course in Euclidean.
That was a revelation to you. That was a revelation.
That was an enormous revelation.
No equipment, no money, nothing. Just
Nothing.
pure thought.
Pure thought, no experimentation. And I decided I want to become a mathematician. I came to my father, who was hoping, at the time I was going to a religious elementary school
In Haifa.
in Haifa, which, by the way, of which my father was the principal. He was hoping I'll go into Jewish studies. The best school where mathematics was taught at the time, maybe even now in Haifa,
Ali.
was the so-called Reali school, founded by somebody, Biram, who came from Germany, and the school was modeled after German high schools, with a strong emphasis on science. I told my father I want to go there, but he said that this is not going to be appropriate because it's a secular and not a religious school. There was also a much poorer religious high school called Yavne. He said I should go there. For 2 years, we were fighting over that, and eventually I had my way, and I went to the Reali school.
This was your 14 or 13?
13. I was 1 year ahead because I skipped a class and I was born in September. But my father also accommodated me by hiring for me teachers who taught me mathematics of, for example, geometry and algebra, even before I went to that school. Now I went to the Reali school, and even if I may say so, I excelled in mathematics
You may say so.
and physics, maybe at the expense of other topics.
But what happened to the biology that you wanted to do?
I completely
The microbes,
gave
the
up.
germs.
I gave up the germs. They were too small for me, too tiny for me. So when I got to 10th grade, I had a wonderful teacher, Elisha Netanyahu, who was a real mathematician.
He's an uncle of our
He's an uncle of,
esteemed Prime Minister.
correct, one of the 6 uncles of Benjamin Netanyahu. So he had, at Biram's urging, he had once a week a math club in the afternoon where we did really more advanced mathematics, including number theory.
This was
serves me.
this was for students or for the general public or
No, for students, for the best math students
at the university or at the high school?
at the high school.
Okay.
And it turned out that even though they were the best students in class, there was an enormous gap in ability between yours truly and those students,
They were much better.
of course. So, for example, he would give each week for next week 6 problems or 7 problems. They would gather and try to solve those together, cooperating between them, and they would solve out of the 7 maybe 2, and I would come with the 7 solutions.
And there was no talk that maybe you should join university classes in an
No,
orderly fashion?
not at the time. But Netanyahu started lending me advanced mathematics books. So even before I graduated from high school at the age 16 and a half and joined the army, I already read both in high school and later on during my army service, I read advanced mathematics,
Give me an example of,
the books.
no, of something that really caused another revelation, some theorem, some...
So, for
Concept.
example, in number theory, Fermat's so-called small theorem, a to the p minus 1, or let's say a to the p congruent to a mod p, was just wonderful.
And this is something you didn't forget years later when you
And they even
got into...
applied
yes,
and
yes.
even used.
We'll get to that. Yeah.
And the generalization due to Euler, a to the phi n, phi of n, congruent to 1 mod n, where a is relatively prime to n.
And what caught your imagination was the beauty of this, the way things stick together.
Yes, yes.
You didn't see any applications at the time.
None.
That came
none,
many years later.
None. Math was just an absolutely pure subject with no... I knew, of course, of the application of math in physics, applications of calculus to physics, but that did speak to me, but didn't make that much of an impression. So, while in high school and during my year in the army, I studied advanced math books lent to me by Netanyahu, and that included Van der Werden's book on algebra, Knopf's book on functions of a complex variable, Knopf's book on infinite series, and several others.
How about geometry and topology? Did that excite you too?
No, no. I was really exposed to topology only when I came to Princeton later on.
And logic and set theory?
Set theory, yes. My sister had an admirer who was a student at the university at the time. She was a high school student, and she didn't pay. She was a very beautiful girl, woman now. And she didn't pay much of attention to him. And so he used to sit there while she was doing her homework, ignoring him, and he would talk to me about math. And he said one day to me, "Michael, do you know there are more real numbers
Than integers.
there are natural numbers? You know how to prove it?" I said, "How?" And he introduced me to the
Cantor, yeah.
to Cantor's diagonal argument, which really absolutely fascinates.
Something else that you used and many people used later on.
Yes, and among the books I read, by the way, was Frankel's book in German about set theory.
And then you actually studied under Frankel at the university.
Yes, later on. That's one reason how I got to it. So I went to the army, and I was in the artillery during the War of Independence, a real shooting war. And I have one maybe curious mathematical story, which I don't fully understand to this day. While I was there studying mathematics, somebody, a very simple guy, who used to be a carpenter in civil life, much older. I was 16 and a half.
He was 18 and a half. Yeah.
No, he was 22, 23 or 4, said to me, Michael, what are you doing? And I said, studying number theory. He said, Michael, do you know what the prime number is? I said, yes. Do you know that there is an infinite number of primes? I said, yes. Do you know how to prove it? I said, yes. Among the books I read, by the way, was Hardy's book on number theory, Hardy Wright, which I already had at the time. So I said to him, I know how to prove it. Do you know how to prove it? And he gave me Euclid's proof. And to this day, it didn't occur to me at the time to ask him, how come you know about that? To this day, I don't know how he came about those mathematical facts. At any rate, the War of Independence ended. I had to serve 2 years, and army service became very boring to me, despite the fact that I was employing at the time also to study math. And I said to Netanyahu, it's there were a way to get me out of here and to get me into the university. So Netanyahu wrote a letter to Frankel, who was a professor of mathematics at the University.
And he is the uncle of Aviezri Frankel
Yeah.
from our department at Weizmann. We mentioned one uncle.
Yes.
So you had two teachers who were uncles of people
Right.
that we know.
So Netanyahu Elisha wrote to Frankel and said, I have this good young man. He deserves to get out of the army earlier. There's no war anymore. And to come to the university. So Frankel invited me to talk to me, and I went to Jerusalem on a weekend where I had leave from the army and visited him Saturday afternoon. So Frankel was sitting in his living room and examining me. And he examined me on number theory, group theory, and so on. Now, at one point there was another young man sitting there who was already studying physics at the university, again much older than I am, relatively much older than I am, and he tried to inject an answer to a wrong answer to one of Frankel's questions to me. And Frankel, who was pretty brutal, turned to him and said, "Idiot, shut up," and continued talking to me. So while we were sitting there, as was customary in those years in Jerusalem, professors used to visit one another. And Gershom Scholem, the famous Kabbalist, who started as a mathematician, came to visit Frankel.
He was eventually the first president of the Israel Academy of Sciences.
Correct. So Frankel says to Scholem, here I have young Michael Rabin, who wants to study mathematics at the university, but according to what I'm examining him and the books he tells me he has studied, I don't see much that he can learn at the university, so I don't know what to do with him. And Scholem smirked and said, well, give him a few volumes of Krelle's journal in German, Krelle's journal of mathematics. He may find new material unknown to him in those journals. At any rate, Frankel wrote to the army authorities,
Got you off the hook.
got me off the hook, and I went to the Hebrew University, and essentially I was admitted into the second, third year, nothing in the first year, calculus and so on, that I could have studied, and I studied for 3 years at the Hebrew University. Now, while there, I concentrated mainly on logic, set theory with Frankel, and I read Kleene's book on meta-mathematics.
But let's just take an imaginary question here. Suppose it was not Frankel who was there, but Frankel was not there. What would have did set theory and logic attract you, or was it just because of Frankel?
To some extent, but it was mainly Frankel.
But you might have gone into analysis or.
Well, as a matter of fact, when it came time to do my master's thesis, I was also very interested in algebra. So I went to Jacob Levitsky, the algebra professor there, who was himself a student of Emmy Noether, and he told me to work on commutative rings. Now at the time, and maybe even now, it is customary that the master's thesis is mostly reading literature and summarizing some advanced articles. But I read Emmy Noether's article on the representation of ideals in commutative rings as a finite intersection of so-called primary ideals. And I found she has proved that every ring with a minimum condition satisfies the intersection theorem. In my thesis, I discovered the precise, necessary, and sufficient condition
Both ways.
both ways for the intersection property.
But the reason I asked the question is because many of us have these almost accidents in life where a particular person influences us, and this has a tremendous impact on where we went. So was Frankel one of those people?
Definitely. And he really kindled my interest in logic and was the reason why I read Kleene's book on my own.
This is what I was asking about, yes.
Very appropriate. Correct. And I suppose had I studied, say, at the Technion, it might have been that I would have gone in a different direction.
What caused you to go to Princeton?
I'll come to that. In Kleene's book, I read the chapters on Alan Turing's work. And I read about Turing machines, and we have to remember that we are talking about the year 1952, or 352. And I realized that Turing machines are really a model for the modern store program universal computer. And that really kindled my imagination no end. And I said to myself, here is a new technology, computer technology, which sprang out, and later on I discovered how much Turing influenced von Neumann, which sprang out from this theoretical study by Alan Turing.
1936.
1936.
So this was about 16 years before.
Yes, correct. And I'll tell you about the connection between Turing and von Neumann in a minute. So I said to myself, there is a technology evolving, and it requires also a scientific corresponding foundation, the same way, for example, that aeronautics is connected to aeroplanes. And that's what I want to do. And of course, computer science as such did not even exist at the time. Now, just for amusement, I had a relative, again, much older than I am, a quite eminent biologist. He met me at a wedding, not my own, but at the wedding of some other relative, and he said, Michael, I understand you want to go to Princeton. What do you want to do there? And I said, I want to study computing as a foundation for the technology of computers. And he said to me, what good are computers? Only to do inventories and some scientific computations and payrolls. It's not an interesting topic. And I said, look, you are a biologist. One day, that was before, by the way, the days of even DNA, computers are going to be employed to construct, to architect, and to analyze very big biological molecules. I had in mind at the time large proteins.
This was before DNA, this
Before
conversation.
DNA. So I had in mind, so somewhat my biological background, I had in mind large
Proteins.
He looked at me contemptuously and he said, that will never happen. So, thus encouraged, I went to the United States on
You were on your own.
on my own.
Yeah.
Yes, I already knew Ruthie.
You had met Ruthie.
Yes, and we decided to get married, but she was studying biology at the time, and she had another year for her thesis.
So she stayed in Jerusalem and you went to Princeton.
And I went the first year to the University of Pennsylvania because that was the fellowship that Frankel got for me. There I had wonderful teachers, for example, Hans Rademacher, famous, and Schoenberg, and somebody called Israel, I forget his last name, an algebraist. I studied a lot of very interesting mathematics. But I knew that the center of computing is Princeton, and I have to get there, and I applied to the Department of Mathematics at Princeton. I didn't realize at the time how selective they were. At the time, and even now, they admitted only 13 graduate students each year. They had a committee that examined the applications. Later on, when I was on the Princeton faculty, somebody told me he was on my admissions committee and he read my algebra paper, which was published in
The if and only if continuation of
the
Eminet's theorem. Yeah.
problem. And that made it, and in fact they admitted me and gave me a substantial fellowship. I don't know if that part of my rendition will remain in the final version, but I came to the University of Pennsylvania. People told them that I'm going to leave them and go to Princeton. The chairman of the department was somebody, to me he looked ancient, he must have been about 60, called J.R. Klein, K-L-I-N-E, who was also the secretary at one time of the American Mathematical Society, and very instrumental in bringing over many Jewish mathematicians from Germany and finding locations for them, jobs for them in American universities. And Klein said to me, why don't you stay here? And I said to him, the fellowship at Princeton is very generous. My wife to be is coming from Jerusalem. I need the money. And then this man, I'll never forget it, said to me, look, Michael, I'm a widower. I had a son who died 2 years ago, an only son, who died 2 years ago in a car accident. I don't need all my salary. I'll augment your fellowship for my salary.
Amazing, amazing. I've never heard this story from you.
Yeah. So
you had to find a different excuse.
yes. So I don't know what I said. I didn't want to say that Princeton, the center of mathematics in the world at the time, is superior in my mind to University of Pennsylvania. Maybe I said that Princeton is closer to New York, where Ruthie was about to be admitted to Columbia University.
So you arrive at Princeton.
So I went to Princeton. I was a student and assistant to Alonzo Church, and I worked on computability connected with algebra. And my thesis, which I did in a very short time, was on unsolvability of group theoretic problems.
Was Kleene there at the time?
Kleene, in the second year of my being a student,
He arrived.
Church was away, and Kleene came from Wisconsin, and actually Kleene was on my PhD exam committee.
I have to tell you a short story about Kleene, who defined the closure star, as we know. He gave an invited talk at one of the Stock or Fox conferences in the early 1980s, and I think it was Richard Stallman who introduced him. He was giving the closing lecture of the conference, and the introduction was, I don't have to tell this audience who Stephen Kleene is. He is definitely the most appropriate star for the closure of this conference.
Wonderful.
So he arrived 1 year after you at Princeton.
Wonderful, yeah. Just for 1 year as a visiting professor. Princeton at the time, I'm sure even now, was a wonderful, wonderful environment with students of mine, half of whom became very eminent mathematicians later on in their career. I got my PhD in record time, in 2 years, and was hired as a fine instructor on the faculty of Princeton. One day, I come to the department, they are all excited, and they said to me, Michael, Kurt Gödel came from the institute in person. Kurt Gödel didn't like telephones. He had that more or less paranoia, and he had the feeling that people are listening to his telephone conversations. So he came in person, and he wants to offer you, he has heard about your PhD, and he wants to offer you a position with him as his assistant at the Institute for Advanced Study. So I went and saw Gödel. I said, I'm very interested. And I came to an agreement with the chairman in Princeton that in my second year at Princeton, I'd spend half a year or more
With Gödel.
with Gödel at the Institute while keeping my fine instructorship. Now, just when in my second year, when I actually have finished already my thesis
So this is 1956.
56-7. IBM decided that they want to have a full-fledged research department. So they sent somebody to Princeton to locate promising young men, at the time it was men, young persons, to hire as researchers at IBM. And it started with a summer job at IBM. Dana Scott came already at that time from Berkeley, where he was a student of Tarski, but somehow fell out with Tarski, so he transferred to Princeton to work
With Church.
with Alonzo Church, and we were friendly, Dana Scott and I. So we both went in 1957 to Princeton, to IBM, and the location was the so-called Lamb Estate, a wonderful collection, while the Princeton laboratory, designed by Saarinen, the Watson laboratory was in the stages of construction. The Lamb Estate, very appropriately, used to be before that an insane asylum. All those buildings where cooks were housed before we researchers came. By the way, we went into the Department of Information Theory. So I came to the Lamb Estate, and then Scott and I joined the Department of Informatics. The people there in informatics at IBM were mostly people in information theory along the lines of
Shannon.
Shannon. And that was under the influence of the book by Norbert Wiener, Informatics. And at the time there was the mistaken assumption or theory that computing is sort of part of Shannon theory, of Shannon information theory. We were actually, Scott and I were actually sort of an exception there. And we had to decide what we want to work on. And we decided we want to work on a limited form of Turing machine. Turing machine where nothing is being written on the tape. So we had the model of what are called finite automata, and then we decided as pure exercises of the imagination to consider all possible variations. One of those variations was non-deterministic automata. That led to the theorem that by use of the subset construction, non-deterministic automata are equivalent in their computing power, leaving out the complexity aspect, are equivalent to ordinary automata.
But I don't want to leave out the complexity aspect. So your construction gives an exponential increase in the size of the state space. But did you and Scott, or Scott, realize at the time that this was also a lower bound?
No, we
You didn't think about
We
that.
suspected it, but didn't realize. But in our work on decision, the paper eventually was called Finite Automata
And their decision
and
problems.
Decision problems. We paid close attention to decision problems and to their computational costs. We didn't have the best possible results. Those came later on, were due to who did that work, not Armanis, Hopcroft. Hopcroft had the best results, but we had pretty good results. Then we also considered, I said, let's consider two-way finite automata where the reading head goes back and
Both
forth.
ways.
And I proved in a very complicated way that these are also equivalent to ordinary automata.
By the way, you mentioned a minute ago that you take Turing machines that cannot write and you get finite automata. But if you take Turing machines that cannot go left, it's the same thing.
Yes,
If they can't go left, they might as well not write at all, so you get finite automata.
correct.
But I just want to insert a comment here for the viewers who might not make the connection. This piece of work that you are talking about now with Dana Scott is what you got the Turing Award for, and this interview is about the Turing Award. And the citation reads, for their joint paper, Finite Automata and Their Decision Problems, which introduced the idea of non-deterministic machines, which has proved to be enormously valuable, and we'll get to that. But the emphasis was on the non-determinism.
Yes, but I'll have a comment on why and how I got the Turing Award a little bit later on. So we also consider two-tape automata, various variations of the finite automata theme. Now, we wrote first of all a technical report, of course, but within 2 years also the paper appeared, which for a while was maybe the best quoted paper in what later on became computer science. Now, a year later, I was again invited to IBM Research for a summer, and Dana Scott didn't want to go there. I went on my own, and while I was at, again, the Lambeth State, John McCarthy, the artificial intelligence guy, came.
Who actually coined the term artificial intelligence?
That's one of his claims to fame, came and posed to me the following problem, which is the password problem. Two countries are at war, and they have their front lines opposing each other. Country A is sending spies across the lines into country B. They have to make their way somehow across the front line of country B, spy in country B, and come back. There is a danger that when they return, their own comrades may shoot them because they may suspect that they are actually soldiers or agents of the enemy. So the way is to give them passwords. But if you give them a password like June 20th, 1932, and you must give the same password to all the guards on the lines, front lines of country A. But the guards are unreliable and are chatty. And agents of country B can discover the password and infiltrate using those passwords into country A. So what do you do? So I had the following idea, which is really first example of one-way functions.
Precursor to the ones used in
Namely,
cryptography.
you take a 100-digit number, that idea is taken from von Neumann. You take a 100-digit number and you square it, you get a 200-digit number. You take in the middle 100, so 50 from both ends, and the middle square is given to the guards. The number itself is given to the agent who's crossing to the enemy lines. When he's coming back, he's being challenged. Who is there? He utters the 200-digit, the 100-digit number. They square it and see if it corresponds to the middle square they have. So I said in that solution that the idea is that calculating the function value, the middle square, is easy, of course certainly using a computer, but on the other hand, given the middle square,
Calculating the original.
calculating one of the origins is hard. Then I asked myself, well, what does it mean that a computable function
Is hard.
is hard to compute? I thought about it, and I found a whole theory, and I found that in parallel to Turing's hierarchy of unsolvable problems and their difficulty, at the time it was already known that there are
So this is Clini.
degrees of unsolvability.
And Clini entered the story there also in terms of hierarchies of unsolvability. Clini's work.
Yes. I found that the recursive functions also have a whole hierarchy of what I called at the time difficulty of computation. So I felt it's very appropriate, of course, for IBM, where they, do and implement solution to computational problems, to have an idea of what the inherent complexity or difficulty, as I called it, is. And I went around the Lambeth State to the people in the information theory department, and I told them of my result, that also computable problems have a whole hierarchy of what is now called complexity.
And from the perspective of 2015, this is really fair to say this is the basis of complexity theory, the origin.
Indeed. So I didn't do the paper, but they, having risen and being educated on the needs of Shannon information theory, very politely in the American style said to me, very interesting, but that had no continuation within that group. I came to Jerusalem, and in 1959 I gave a lecture on that, what is now called complexity theory, and in 1960 I wrote a report, or in our research report,
Degree of difficulty of computing.
a function. Now, how does that connect to my Turing Award? In 1974, after I was rector of the Hebrew University, I was on sabbatical at MIT, and I got a call from Don Knuth. He didn't tell me the purpose of the call, but he said, Michael, I'm now interested in the origins of what is now computer science, and I know that you have written a very interesting early paper in 1960. Actually, Michael say, the work was done in 1958 on what is now called complexity of computations. Can you send me a copy? Which I did. Months later, I get a telephone while I'm at IBM Research during the summer. I get a telephone call from Joe Traub, who unfortunately passed away a few months ago. So now, unfortunately, the late Joe Traub.
He was at Columbia.
At the time, he was still at Carnegie Mellon. But when he died, he was a
Oh, he's been at Columbia for many years.
Yeah. So he tells me that I got the Turing Award. I ask him what about, what for, and he says for your work on finite automata and your work on complexity. When my getting Dennis and my getting the Turing Award was announced in the communications of the ACM, they also say and mention explicitly the work on complexity, saying that it was the first paper on complexity theory. Somehow, maybe unfortunately, it didn't make its way into the citation. The citation was done by Geller and maybe decided for reasons of symmetry between Dana Scott and myself to mention finite automata, and just to say that we had later on, each of us, not joint but interesting work. At any rate, there is
Traub plays another role in our story here.
I'll come to that.
Yeah.
I'll come to that. So I want to come back for a moment to Alan Turing and the modern computer. While I was at IBM, not the first visit, but later on, the head of the mathematics department, where I visited twice for a year, and also during many summers, was Goldstein, Hermann Goldstein. Hermann Goldstein was a close associate
Von Neumann.
of von Neumann. They were together before the war on operators on Hilbert spaces. But during the war, Goldstein was at the Aberdeen Proving Grounds, and von Neumann was with him, where the trajectories of cannon shells were mapped for the American US Army. Now, at the Moore School of Electrical Engineering, Mockley and Eckert built a computer that was used to do calculations of those trajectories. By the way, I've been told that Eckert and Mockley developed that computer in order to be exempt from active army service in World War II.
That's also artillery.
Yeah. Be that as it may, Hermann Goldstein, he told me, took von Neumann to view that primitive computer which filled several rooms and broke down every half hour or so. Now, that computer was being programmed by turning switches and connecting
wires,
electric cords, and also maybe using cards, punch cards. Now, that computer had a memory, electronic in those years, also built on radio tubes, where they were keeping information about the resistance of air to artillery shells at various temperatures and various air pressures. And they stored there several thousand numbers like that. Von Neumann looked at that memory and said to them, why don't you, in order to accelerate and make it easier to operate your computer, why don't you store the program in this memory?
So that was the first allurance to stored memory,
Yes.
stored program concept.
And then when he came back to Princeton and was building his computer, the Joniac, later on called the Joniac, of course that idea of a stored program came in. I never met von Neumann, even though I had a letter of introduction from Frenkel to von Neumann, but I didn't want to bother such a very important man at the time. But I spoke a lot to people who worked with him on constructing the Joniac. And they all told me that von Neumann was deeply influenced by the Turing work. Actually, Turing in 1937 was in Princeton for a year or two and interacted with von Neumann, and that many of the ideas of the Joniac were an implementation of the 1936 Turing machine.
In a way, the stored program concept is really a manifestation of universality,
Correct,
which is Turing.
Correct. One computer which, by being appropriately programmed, in fact by stored program, can compute any computable function. So they also, now that's an insight about von Neumann, they were people who spoke to me were electrical engineers. Of course, the construction of the computer involved a lot of electrical engineering work and the design of various devices, switches and so on. They told me that whenever they got into a design problem that they could solve as electrical engineers, they would come to von Neumann, and within half an hour he would solve the problem for them.
Amazing. Yeah.
Tells you something about
So we're
that.
getting closer to probabilistic computation now.
I'll come to
Oh, you will? Okay, good.
I'll come
Good.
to that. So I came to Jerusalem and I continued work in mathematical logic model theory on the one hand, but also computability on the other hand. Now, in the mathematics department, there was no appreciation of the work on computing. In fact, now it's being slowly changed. and
But it's
modified.
still like a stepson
A stepson. And the mathematicians,
in the eyes of mathematicians.
the mathematicians don't really realize that the mathematics of computing, or what's called computer science now, including computability, complexity, proving correctness of programs and so on, and the list is long list of highly intellectually
Logic.
significant-
And logic too.
and logic, that this is a development of mathematics which is equivalent and had as much impact on our real life today as Newton and calculus and Lagrange and Laplace had at the time on physics and the 19th and
And engineering.
beginning of 20th century mathematics. A new kind of extremely significant and impactful mathematics. At any rate, I continued working on logic. One benefit I had was brilliant students like Saharon Shelach, who at the time was maybe the supreme logician in the world. At any rate, I also brought to Jerusalem the work on automata theory, including work on push-down automata and the relation to context-free languages. Noam Chomsky knew of our work, and of course the push-down automata that define all
Context-free languages.
context-free languages are inherently, in order to get all of the context-free languages,
Non-deterministic.
are non-deterministic, and Chomsky completely acknowledges his and Schützenberger's debt to us for the concept of non-determinism. Now, there was a confusion at the time between non-determinism and probabilistic behavior. And actually, probabilistic automata are not really non-deterministic automata. I knew that I wanted as a next step, as one step, to develop probabilistic automata. Ed Moore at Bell Labs was interested in finite state machines, himself wrote a very important paper on the topic, and invited me to spend the summer there.
These are Moore machines.
Moore machines. So I came there and I settled the problem. I defined probabilistic automata and a number of very significant results. One being that under certain limitations on probabilistic automata, they actually also only define regular languages,
But much smaller.
are not more powerful than deterministic and non-deterministic automata. The other significant result is that by the introduction of probabilistic behavior, in some instances you get enormous simplification of the automata, and that automata with a relatively small number, probabilistic automata, with a relatively small number of states can define regular languages which can be accepted or defined only by classical automata with a much, much larger, exponentially larger number of states.
But this is true also for non-deterministic automata with respect to deterministic
Yes.
automata.
But non-deterministic automata cannot actually be
executed,
constructed, whereas probabilistic automata can be easily constructed and actually also simulated by use of appropriate matrices, stochastic matrices, can be simulated on computers. So that was actually the first example that the introduction of probability and the probability of error into computing actually results in a very significant
Improvements.
improvement in performance.
This was 1965, 6?
No, this was 1960. The
1960.
paper appeared maybe later on, but the work was done and the report was written
Yes.
in 1960, while I was at
Bell Labs.
Bell Labs with Ed Moore.
I'd like you to say a few words about the S2S
I'll
result.
come to that.
Yeah, you'll come to that too. Okay.
I'll come to that. So I continued the work which much of the time combined logic and automata. Now, Elgot,
Calvin Elgot.
and Büchi used non-deterministic finite automata to decide the second order theory of one
Successor.
successor function with quantification over finite sets. Later on, Büchi, on his own, showed that the second order theory, quantification of arbitrary sets of one successor function, like x and x plus 1, the function x plus 1, is also decidable. And I put to myself the question, what about decidability of second order theory, quantification over arbitrary subsets of the theory of two successor functions?
But you have to explain to the viewers why this is an important question.
Yes, I'll come to that. So the model is, for example, an infinite tree. It has a root. Every node has two successors, a left successor and a right successor, and you have quantification over arbitrary subsets of the nodes. I realized
So going to two successors is going from strings to trees.
exactly. And of course, once you can do that, you can even have any number of
Of course.
within that theory, you can have any number of finite and even countable number of successors. You can model it within that tree using subsets. Now, I realized that this is actually very powerful theory. That if it turns out that this is decidable, then you can decide many problems in logic which at the time were not known to be decidable. For example, the theory of Boolean algebras with quantification over ideals, and many other examples. The theory of all sorts of orders, theory of orders, and so on.
And logics also, tense
and
logic and model logics.
Yes. So in fact, I started working on that problem, and it was clear to me that I need a concept of necessarily non-deterministic automata on infinite trees. And the question is, what is the appropriate notion of acceptability? You have a run, so-called, of the finite automaton on that infinite tree, and the question is, how do you define acceptability? And it turned out that the acceptability notion was of a new kind. But you had to prove that these definable sets, acceptable by these finite automata on the infinite trees, that these definable sets are closed under union, intersection, and complementation. Union and intersection were trivial. Unions and intersections were trivial. Complementation was the big unknown. In the summer of
69.
in the summer of 1966, Mostowski from Poland visited Jerusalem to work with me. I told him what I'm working on and all the many positive decidability results which will be a consequence of a full theory of finite automata on infinite trees. So I remember we were standing next to the math building in Jerusalem, and he said, Michael, since it has so many positive results, of so many decidability problems, some of which may in fact be undecidable. What you should do is prove the negative of what you are conjecturing. And I said, well, I'll devote some limited time, and if I succeed, then I'll have this wonderful, powerful, most powerful result. So I was hired again for a full year by Herbert what's the name we had before?
Where? Moore?
No, not Moore. At IBM.
I,
Collaborator for Neumann.
Goldstein.
Herbert Goldstein. I was hired to spend a year at IBM. And I said I want to work on that problem. And I put to myself a limit, I forget what, 3 months, that if I don't succeed, I'm going to give up that problem. So I used to work every day very intensely on this problem, drawing these trees. My daughter Tal, who is now herself a well-known cryptographer, computer scientist, was at the time 5 years old, and she said to me, "Daddy, why are you drawing all these wigwams?"
Wigwams.
Because the trees, of course, I do only palm trees, looked like wigwams.
So and then you were able to prove your wigwam theorem.
I was able to prove my wigwam theorem, and the problem was so difficult that every morning when I came to IBM and to start my work, and I usually work in my head. In fact, at IBM, it was already in the new building, in the Watson Research Lab. I used to walk the corridors and think about
The long round corridors.
round corridor
Sickly
next
corridors.
to the window.
Yeah.
So it would take me an hour to reassemble all the components of the construction and the problem and the lemmata I want to prove, to reassemble it in my head. And only then could I start working. What was interesting about that work was it is a very difficult result. Many people consider that to be the most difficult result in mathematical logic.
I'm a fan. I'm a big fan of that theorem. Not only because of the applications. It's also a very powerful and beautiful decidability result. No
Thank you
doubt.
very much. What was
But I must ask you before you go on. What do you think of the later proofs?
I'll come to that.
Oh, you'll come to that too. Yes.
I'll come to that.
This is the theme of this interview.
Yeah, I'll come to that. So it turns out that one interesting and very remarkable aspect of the proof is that even though I am dealing with essential, finite automata, there are tables of transitions and so on, and also the notion of acceptability is defined by reference to finite subsets of the sets of states. So even though it's all finite, and even though structure itself is countable, it's that binary, not countable, that binary tree, but the depth
is countable. Yeah.
The proof itself uses Zorn's lemma, or could use transfinite induction. And the student of mine in Jerusalem has shown that the transfinite induction goes all the way up to omega 1, all the way up to the first non-countable ordinal. So this is a strange mix of the finite and the non-countable infinite in the proof. So the first simplification of the proof was by a student of Hartley Rogers, who's now professor at, what's his name? The first concept of zero-knowledge proofs is Goldwasser, Micali, and
Rakoff, Charlie Rakoff.
Charlie Rakoff.
Yeah, I remember
and a
that
very
paper.
nice, elegant proof. The next proof is due to
Safa.
no,
No.
is due to this Russian mathematician who's now at Microsoft,
Yuri Gurevich.
Yuri Gurevich, and a Berkeley logician. But if you look at these proofs very closely, they also essentially require
Something
transfinite
transfinite,
reduction.
obviously.
And up to omega 1. So I think that basically they are the same, they are simpler.
But
to
even
understand.
if they're not, simplifying a proof, the proof of a great theorem, doesn't degrade from the theorem or from the proof, or the original proof at all.
Thank you.
Let me ask you another question about this. Suppose an imaginary question. Suppose you did not get the Turing Award in 1976 for finite automata or for the origins of complexity theory, and suppose what you know now about the Turing Award and what kind of things it's given for, would you have awarded the S2N, this decidability theorem, is that a Turing Award level piece of work in your opinion?
I would say yes, A, and B, certainly in combination, though they are different with randomized, what are now called randomized algorithms, to which I'll get in a minute. So at any rate, I had that result about automata on infinite trees, and I was really very pleased with it. Ruthie, and I had at the time already 2 daughters, went back to Israel. I stayed at IBM, and I wrote the paper, which appeared
1969.
in 1969, but was written in 67.
So we've reached 1969 and the publication of the paper on the
S2S.
S2S.
So, among other things, I started to think about, not to work, but to think about artificial intelligence. And at the time, in part also following the S2S paper, people were trying full steam to implement programs for deciding various logical theories, but deciding them in practical time. I was dubious about whether for most theories, full theories, you could have a practical decision problem. Let me mention in this context the result that I did with Michael Fisher. Already in the 1930s in Poland, a student of Tarski proved that the theory of addition, just addition of natural numbers, is decidable.
This is Presburger arithmetic.
And it's called Presburger arithmetic is decidable. Now, Mike Fisher and I proved that even though decidable, the complexity of it for some statements is doubly exponential. So there is a constant lambda, not very small, maybe 1/2, so that essentially for every n, maybe n bigger than 50 or 60, there are statements of Pressburger arithmetic of length n, whose shortest proof, never mind deciding whether true or not, shortest proof is of length 2 to the 2 to the lambda n. So that's quite devastating. And I started thinking about how to get around it. And maybe under the influence of my probabilistic automata paper and the impact it had, positive impact it had on complexity of
Size of the automata.
recognition of regular languages, I decided to see how probability might help. And I had two variations. One variation was, and I think that is very valid to this day, to say that, well, maybe, for example, the Fisher-Rabin Pressburger arithmetic examples are really quite unnatural and are deliberately constructed to get devastating complexity results. Maybe that on
average,
problems are not very hard. And that may well be the case, though I have somewhat modified my idea about that. So I talked about these probabilistic theories that was taken up by mainly Descartes, who, for example, proved that for various, at least two-dimensional shortest path problems, the average case is not really very hard. And I don't go into details of what the exact result was. The other avenue I was considering was using probability
inside the algorithm.
inside the algorithm. Very good, very good. I didn't think about this turn of language, in order to get results which are true always, but with a certain small, very small probability of getting a wrong result. So for any particular problem, you are getting the correct result quickly every time,
And surely.
and surely subject to probability of being wrong, which can be made exponentially, very easily exponentially small.
So if it's a decision problem, saying no is true and saying yes is true with very, very high probability.
Yes. So I had an example which by now is maybe vacuous, namely, at the time it was not yet known whether Fermat's big conjecture is true or not. And I had this mental game of somebody coming and saying, here I have 4 numbers, x, y, z, and n, each of them very, very large, each of them with thousands of digits, and I claim that x to the n plus y to the n is z to the n. And the person claims, I've proved that equality, falsifying a counterexample to Fermat's last theorem. And now, the numbers are so large that even by approximate computations, no matter how many digits you do in that approximation, you get agreement. However, by using randomness and using randomly chosen prime numbers, you are able, not very large prime numbers, also prime numbers of just a few thousand digits, no, a few hundred digits, you are able to show him wrong, because mod p, it turns out that this is not equal. So that was a proof of, in this case, a negative result by use of randomization and greatly simplifying the computation.
But of course, there is a philosophical issue here, which is, suppose that was done, can you put QED at the end of the proof, or it has to be QED with probability 1 over 2 to the
Yeah.
power 100?
So I'll come to that in a minute.
Oh, again, we're going to
With
come
an
to it.
amusing story. This brings to mind an amusing story. So I had that, and I gave a public lecture in 1974 in Stockholm at the annual meeting of the, I forget how the International Congress on
must-
Computer Science, EHOOPS,
EATCS,
EATC,
the European.
not
no,
European, the world, EHOOPS.
EHOOPS, maybe, yeah.
Yes. Anyway, I gave that lecture. There were hundreds of people present, and the lecture was on the natural limitations of artificial intelligence. Then I was at the time in an administrative position as rector, academic head in the European sense of the Hebrew University. In 1975, I finished that position, and I went for a year
MIT.
to MIT for a year. At MIT, I met
Gary Miller.
Gary Miller, who found a polynomial time algorithm for testing primality, which was based, however, on the extended Riemann hypothesis, which to this day is still an open problem. And I said to myself, can I use probability in order, now I call it probabilistic algorithm, but randomization in order to settle that question. And I found, unknown to me, that Solovey Strassen were working on the same problem at the time. I found a simple randomized algorithm for testing primality.
Getting around the Riemann,
Not using
not using any unknown problem.
And in fact, essentially only using our old friend
Euler,
Fermat's-
Fermat.
Fermat's theorem, which was very satisfying. So I also used the method to to simplify solution of another problem. Suppose you have a finite number of points given by their coordinates and in the plane, say, and you want to find A or the A nearest pair, 2 points Pi and Pj given by their coordinates xi, yi, xj, yj, so that the distance between these 2 points
Shortest.
is the smallest among all possible ends, and choose 2 distances. Now, people had a classical algorithm solving that problem in time n log n. I have shown that by using randomization, you can solve it in time O(n),
Linear time.
constant times n. I gave a lecture in 1976 in January at a symposium organized by
Traub, our
by
friend.
Traub at Carnegie Mellon. And the paper appeared in the book of that symposium. After the lecture, I went down, and maybe 20 people joined around me and said, well, this is very nice, but really very limited in scope. Because the concept you used for the primality test, which is witnesses to compositeness, not to primality, to compositeness, is really only appropriate for that problem.
Idiosyncratic.
Idiosyncratic, very good. And only Joe Traub, and amongst these 10 or 20 people, were some of the most famous computer scientists at the time, some of whom are still very alive and very famous today. Only Joe Traub said, no, this is a groundbreaking idea which is going to change the use of randomness in algorithms, inside algorithms, is going to change the face of computer science.
So, getting back to my earlier question, had there not been a Turing Award, this pioneering work on randomization, you would give yourself a Turing Award for that? If you and your
my
wife,
daughters would certainly, and you as well, would certainly give me a Turing Award for that. No, I think this really changed the field.
I agree.
So then I went on and found numerous applications of randomization. And speaking, of its non-acceptance, so there was the randomized algorithm for testing primality. At the time, there was a mathematician in Berkeley who was testing numbers for primality, but numbers of a special kind, so-called numbers of the form 2 to the p minus 1.
Your P is prime.
Where p is prime. So he did and tested very large numbers. He didn't like the new approach. And Joe Traub, who spent the summer after my lecture at Berkeley in '76, said that he was in the Berkeley Math Computer Science building in an elevator with that mathematician and other mathematicians, and they were saying Rabin has this randomized test for primality. So the guy very angrily said, a number is either prime or not, which, by the way, I also accepted
Of course.
in my analysis, or not, and randomness has nothing to do with it. And even though the math department was on the 7th floor, he pressed the elevator and left
the elevator.
on
So
the
that's
second floor in great anger.
That's a nice story, but I'd like you to respond scientifically to the fact that a deterministic algorithm for primality was later discovered. How do you compare?
Well, the
constants too large.
People programmed it to check a number of the order of a few 100,000 or maybe a few million, not digits, but of size, a few million, by the Indian test, takes hours implementing the Indian test. Whereas
You mean running the test on this particular?
Yes. Whereas using my test, which by the way is 8 times faster than the Solovay-Strassen test, is different and faster by a linear factor than the Strassen Solovay test. You can test the number with a few thousand digits in a fraction of a second.
Very, very fast.
In fact, I would sit in class, explain my test, and my assistant would sit there with his computer, Alex Healy, and I would say to him, let's choose a number which we would define not by giving all the digits, but a number which is equivalent, is actually a number with a few thousand binary digits, and he would come back with the answer prime within more or less before I finished the question.
But personally, did you feel a little tinge of regret when the Indian three author test was published? No, this is fine with you.
Not at all, and the whole thing didn't have any further
Application. Well,
they may have worked on PNP at the time, but nothing, no results came. So we had these very many applications of randomization. Let me mention oblivious transfer, which also uses randomness. In 1980, I went to Atlanta, Georgia, and I'm getting stuck on names. Somebody there asked me the following question. In 1980, there was the Iranian-American prisoner exchange, in return to which the Iranian bank accounts that were held frozen in various places were unfrozen, and they got their money. So the person said to me, how can you make sure that, say, the Americans get their hostages and then don't release them the money, or the other way around, the money is being released and they don't release the hostages? And this was done at the time by use of trusted third parties. Can you do that without trusted third parties? So he asked me that question in the evening. I went back to the hotel, slightly drunk from the wine we drank at that dinner, and I came up with a solution. And the solution used the following seemingly impossible construct, which later on I named oblivious transfer. Namely, I have a secret and I conduct a protocol with you, and at the end of that protocol, with probability exactly 1/2, you either have or do not have the secret. You of course want to get the secret. You either have it or don't have it, and I have no idea whether you got it or not. A generalization which follows from my version is that I have 2 secrets, and you know that one secret, say, is the password to safe number 1, and the other secret is the password to safe number 2, and those safes are at the bank where I don't have access to, but you do, and you know that safe number 1 contains certain documents you are interested in, safe number 2 contains other documents you are interested in. And you can conduct a protocol with me where you choose to get secret 1 or secret 2, and I'm assured that you got one of them.
But you don't know which one.
And I don't know which one, and and I'm sure that you have not one bit of the bit.
That's a precursor to zero knowledge.
Yes, correct. So I invented oblivious transfer. At the time, I was already a visiting professor at
Harvard.
Spending half a year at Harvard and half a year here in Jerusalem. So I continued working. There's one topic, yes, there's one topic that I still want to mention. Maybe in 81, I was sitting in Jerusalem at the faculty club, which is called Belgium House, with
Mickey Ben-Or?
No,
No.
not Mickey Ben-Or. Sitting with, again the block, Dolev.
Danny Dolev.
Dolev, and I asked him, Danny, what are you working on now? And he said, I'm working on Byzantine agreement. I said, what? What's that? And he explained Byzantine agreement to
And the relevance to distributed computing.
and the relevance to distributed computing. In fact, he was working with Ray Strong very intensely at IBM. They were extremely interested in distributed computing in connection with the system they were developing at the time for air traffic control. So it also already at the time had significant practical application. And the main result, there were two main results due to the people who invented the concept. The one result is that if in N, say 100 participants in the process, there are more than a third ones who may want to throw disorder, more than a third Byzantine agents, then agreement amongst the good ones is impossible. And that result is absolute and not very hard. And then that if, let us say, 30, or let's say in 300, if 95 are possibly Byzantine, then you need 96 rounds of exchanges of information in order to reach agreement under those adversary conditions. And the other result was that if these exchanges of information are not governed by a synchronous time clock, then agreement is impossible.
And then you started working with Danny Lehman or Mickey Ben-Or, no?
No. I went home, and the next day I came to Dolev and said, A, if you use randomization, a common coin which you can create, and I had a way of creating a common coin for the agents, then you can reach agreement in 6 rounds, no matter how many.
Even more than a third.
No,
No.
not even more than a third, but no matter how many Byzantine agents there are.
That's what I said.
A. B, my solution also works in the asynchronous case. That was later on improved by, chiefly, by the way, Tal, my daughter, in her PhD thesis, and Ran Canetti, they worked together, to 3 rounds. But the main result was breaking away from the classical lower bound, Byzantine agreement lower bound. So for that resulted years later, in addition, of course, to the practical applications, in the Dijkstra Prize that I obtained
Last
just a couple of
year.
months ago. And Ben-Or independently used randomization to reach Byzantine agreement, but he didn't have results as sharp as the ones I had. And okay, that was one. Let me maybe finish by talking about
Zero knowledge.
zero knowledge proofs. So zero knowledge proofs are again one of these absolutely incredible constructs created by computer scientists. Suppose I know a secret which is a solution to a certain problem. Let us take, and this is not really the most general case, but let us say that there is a key to RSA encryption, the key being the product of two prime numbers, and public is the product, which is the encryption key, and I know the secrets because I've created that public key. I know the two prime components, two prime factors. Now, I can prove to you that I know the two prime factors without revealing anything to you.
Zero knowledge.
Zero knowledge, and that's zero knowledge which is extreme. Not only that you don't know when I finish the proof, on the one hand you are sure that I know that secret, you don't know anything about the secret, neither do you know anything else that you didn't know before independently.
Just
Like the name, the maiden name of my grandmother.
so just to make this sharper, I get to become convinced that you know the secret with a probability that I can choose,
Yes, also.
and I don't know anything about the secret itself that I cannot find out in polynomial time on my own anyway.
Yes. Neither about the secret nor about anything else.
And we should mention, of course, Micali and Goldwasser, who got the Turing Award a couple of years ago for
Yeah.
among other things, for
So
this.
the original result was Goldwasser,
Micali,
Micali, and
Rakov.
and they did additional work and got the Turing Award. That work is extremely important. However, the original zero-knowledge proofs are not really very practical. And for example, and I'll give the application where what I did became very practical. So I found a version of general zero-knowledge proofs, which is basically based on the following: that I'm using numbers which I break into the sum of two numbers. Like, for example, I can break 17 into the sum of 22 minus
5.
5. It's not really the way I do it. And I encrypt each of the components separately. Now, in the proofs that I have, I always reveal Rabin's 11th commandment is never reveal both components of a hidden number. And it turns out that by use of that method, you can generate very practical zero-knowledge proofs for very important practical problems. So in 2009, that was published in a paper together by me, together with Thorpe and Servideo, published in 2009. I think published in 2009. And the people at Google heard about it, and it turns out that the people at Google, it's not obvious, are deeply involved in auctions. We had in that paper an application to the following problem. Suppose I conduct an auction and several agents Goldman Sachs, Bank of America, whatever, submit bids for the item, say the Empire State Building. Or let us say I'm the US government, I conduct an auction for drilling rights in the Gulf of Mexico. And various oil companies submit bids. Now submitting sealed bids means, instead of closed envelopes, that each of them chooses a key of his own, encrypts the sum of money, and hands it to me. On Monday morning at 10 o'clock, the auction is closed. Everybody sends me his secret key. I decrypt all the bids, open all the envelopes, so to speak, and say who won. Now, nowadays, because other people, if I say British Petroleum won, maybe the president of British Petroleum is my cousin, and I'm actually cheating. So they want to see all the keys, and they want to see all the bids. So it is customary in auctions to reveal the bids. Now there are also very important reasons for not revealing the bid values. For example, going back to the oil drilling example and locations, each of the bidders has their private information by experimental drills for the value of these locations. And British Petroleum
They don't want you to know, of course.
For the next auction, doesn't want Exxon to know how they value certain locations in the Gulf of Mexico. So already in the paper with Thorpe and Servideo, we suggested that the bids in the closed envelopes are being posted, but they are being posted in the split value mode. And then the auctioneer, who knows, of course, what the bids were and who won, can also supply, using a split value, a proof for the correctness that this bid was
the highest, although giving away no information.
Giving away no information. Now, usually, maybe it's the sales price itself is going to be revealed, but the other bids are going to remain secret. So it turns out Google is deeply involved in auctions, namely those locations. When you say type in Paris, they know a lot about you, and they know that you are a very fairly wealthy person, and that you may type Paris because you want to go there. So various
They auction advertising space. Yeah.
Advertising these clicks.
Yeah.
So they auction hotels, airlines, travel agents, and whatever, maybe fancy stores in Paris. Now, each of these agents has an agreement, a signed agreement with Google, how much to bid, say $1, for each of these locations, depending on what the bids, what the buyer, who the buyer is. However, at the end, they may want to know, if they are told that they didn't win, they may want to know, at least in sampling, let's say, one auction out of 100, whether the announced result is legitimate and honest. At the same time,
they don't want to give away
American
information.
Airlines doesn't want another airline to know how they are bidding. So this technology allows this sort of secrecy preserving, zero-knowledge proofs of results of auctions. And while at Google, I say IBM because I spent so many years and summers there, while at Google half a year, I wrote a joint paper that they insisted I be the main author with Mansoor, Muthukrishnan, and Moti Jung, where we gave a much more efficient version of these general zero knowledge proofs.
When was this published, this paper?
And that was published in 2012 or 13 in the proceedings of the European equivalent to StockFox,
EATCS,
whatever, yes.
Theoretical Computer Science.
Yeah, yes, yes.
Maybe ICALP.
ICAL.
ICALP.
Exactly, ICAL. The one who gave the lecture was Moti Jung.
Moti Jung.
I couldn't travel at the time. So now, and with this I think I'm going to finish.
No, I have some questions to you
Yeah,
still.
yeah. There is a classical problem in auctions which has to do with second price auctions. Let me explain. Actually, one very efficient mode of auction was used in practice, suggested by a guy called Vickery, and they are sometimes called
This
Vickery.
is second bid winner?
Yes. So the one who wins is the highest bidder, but the price he pays is
Second.
the second highest bid. Turns out, and Vickery has proved, that this type of auction has great advantages for the seller because it induces, in case of honest auction, induces everybody to bid his true value for the item which is being auctioned. I'm not going into the proof of that,
No.
but it's not very hard. However, it turned out that in many important auctions, where Vickery auction, where this model was tried, there was a collusion between the bidders, or maybe the main bidders. Namely, the auctioneer has a reserve price. He's not selling this item, this Renoir or whatever, for less than $10 million. Now, the bidders get together and they have a conversation. It's illegal, so they do it in Bermuda. It's illegal, but they decide amongst themselves. They find out, and he may be lying to them as well, who is going to be the highest bidder. And he says to the others, I'm going to make my highest bid, and you'll all bid very close to the reserve price, and then I'll get the Renault.
But I'll only pay
I
the...
only pay the reserve price. And the seller is being cheated in this way. This happened several times. People went to jail. And it seemed that there is no way of preventing this kind of collusion. Now, using these modern new zero-knowledge proofs, Michali and I, a year ago, solved the problem and have shown that there is a way where collusion can provably be prevented. This was looked at also by major economists who do design of mechanisms for bidding, and was approved by them as well. So
that's
solved
beautiful.
an open 40-year problem.
And if I may add to this, so this paper on Vickery auctions with Michali was published about a year and a half ago.
In the proceedings or
This is not the
communications
yeah.
of the ACM.
Wherever. And so you, if I might say, were 83 years old when this was published.
Yes.
And so this is quite amazing.
Thank you.
I wish there were many more scientists who, at the age of 83 and still going strong, despite some recent health issues, are still going strong. I have a few questions, kind of to wrap this up.
And I want to make a eventually closing remark about computer science and mathematics on the one and computer science and science in general.
Well, so you're intercepting two of my questions, but let me ask. First of all, one comment I wanted to make to complement something that we spoke about earlier. The S2S theorem has implications which we did not really mention, not only on decidability of theories and logics, but has profound implications in computer and program verification, which we did not get into, but it's really worth mentioning, verification, synthesis, and so on. So my first question to you now is there anything that you feel sorry that you did, or something you feel sorry that you didn't do or didn't do in time?
So,
in this long career?
no, I don't really feel sorry about anything I did. I feel sorry that there's one problem I'm still working on that I didn't solve, and I just don't want to say what that problem is. But I'm thinking about an application of randomized algorithms to a major problem, which I still hope I may do. Now, one thing...
I'm not going to try to coax you into saying, but
No.
is it in the general area of e-commerce, blockchain computation,
No.
and things like that? Okay.
No. And I feel sorry about something I didn't do when I was rector of the university. There was a student revolt similar to the ones in Europe while I was rector of the university. And I was able and they actually took over the Senate.
Early 1970s.
No, 1975.
Yeah.
Took over the Senate. I went in, and police cars unknown to the students were circling the university so that in case the students were trying to seize and throw me down the window, the police hopefully would burst in and save me. It wasn't necessary. By the way, I also took off my watch and gave it to my assistant in case that they throw me down, at least the watch will remain. Now, two of these students who were applying to the university and who weren't admitted, and these were students from a poor neighborhood in Jerusalem. After I settled the student revolt and sitting in the Senate hall room, University Senate room, went into my office and were sitting there in a sit-in. And they were sitting there for a whole week. And they were telling me that despite their poor grades, they wanted to get into economics. They'll, if admitted to the university, if I say the word, they'll be an academic success. So they were sitting there for a whole week, and I was making sure they had food brought in and so on, lunches, meals brought in, facilities to bathe, and I would conduct meetings with people who came to see me while these two students were sitting on a couch next to them in my office listening in. Now eventually they left without being satisfied. And later on I thought, I could have admitted them. At worst, they would have flunked out a year later.
Yeah, yeah.
I should have.
A short question. I know personally, and many of the viewers know, that you also give wonderful lectures and you write very, very lucidly and clearly. Why did you never write a book?
Well,
Not that we write books, all of us, but you could have done this.
well, the answer is manifold, and it's not easy to present that answer to you, who, if I may say so, wrote such wonderful, wonderful books, for one of which you even got, I forget the name of the prize, but
ACM Karlstrom. Karlstrom.
Karlstrom Prize. So, when I was working on the automata theory, I thought maybe I should write a book on automata. But you know, with the passage of time, automata is very important now, but a book I don't think would have such an impact. The one which would have had an impact would have been a book about randomized algorithms, the various aspects, including, for example, Byzantine agreement and the applications to number theory, cryptography, zero knowledge proofs, and so on. I must say that I don't have the persistence and maybe the patience.
Yeah, it is hard
to
work.
put- And at the time it used to be pen to paper, now to be finger to computer.
But if I may make a modest suggestion, I don't think you want to sit down now and spend 2 years writing a technical book or an introductory textbook. But I would try to encourage you to write a small monograph on your ideas about computer science and mathematics and their future. Because my next question to you was going to be, don't give me your manifest yet, but what, in your opinion, are the two most promising directions that young researchers should get into in computer science? Just say two.
Well, I would say very large databases of the Google type, which are going to be employed, however, not very generally, but in specific fields. And that combined with certain decision processes, not unlike Watson by IBM, but applied, say, to medicine. So that, for example, if somebody comes to a doctor with certain symptoms, the doctor can consult, and the doctor suspects some heart problem or maybe some dementia. The doctor can go and consult the database where maybe 200, 400 of the most important experts in this field give him information and also suggest to him various solutions. So, very large databases of that form. And that really combines databases and various decision procedures. The other direction is computer modeling. And this is certainly not a stranger to you. I feel that there are certain systems, economy being one of them, and certain biological systems, maybe the human body, maybe the brain, or even certain parts of the brain, that are so complicated that the classical mathematical approaches are simply insufficient to really describe, analyze, and produce reliable results. And we know that in economics, there are mathematical economists who come up with completely contrary to each other proposals and solutions to existing problems. And the solution, the practical solutions may be to have very large-scale modeling where a lot of that data is being collected and its evolution in time is also being collected. And from that, by some methods, which maybe as yet are not yet completely clear, and by the way, are not maybe universal. The method in economics may be different.
Might be specific,
the
yeah.
method is maybe
Domain specific.
Thanks. Then some predictions and some insight, but reliable insight, will be gained without going really beyond our human, now current and even future human understanding. And I'm sure this is going to happen.
One more question. As one of the two fathers of non-deterministic computation, you and Dana Scott, and as the father of several other fundamental things in complexity theory, quick answer. What do you believe? P equals NP or P not equals NP?
I'm undecided on that.
Do you have a feeling? Do you have intuition?
Very difficult, very difficult. I'm going to refer to a conversation I had a long time ago, also in Belgium House, as it happens.
Belgian House is the coffee place at the Hebrew University, next to the computer science building.
Yeah.
The round
It
building.
used to be the computer science building. Meantime, we have moved. So I was sitting with Noga alone, and we were discussing P versus NP. And Noga alone said, maybe he now is going to be of a different opinion. At the time he said, you know, we don't know everything about algorithms. From time to time, maybe every decade, maybe every 2 decades, some new type of algorithm, some new methodology in algorithms, maybe he had in mind, for example, randomization, comes up, which allows efficient solutions to problems which before had inefficient solutions or maybe no solutions at all. And PNP can be an example of that. And therefore it's possible that P equals NP in the style that non-deterministic automata and deterministic automata are equivalent, except that now we see no way of doing it. But I'm sure that if it somehow gets settled, 2 remarks. First of all, I think that if P is not equal to NP, then we are miles away from a solution. And all the current impossibility methods really only scratch
The surface.
The surface of allowing us to prove, if true, that P is not equal to NP. If P is equal to NP, I would say in that case the solution may come up in the coming, say, 2 decades, more likely.
Before we wrap up, do you want to tell us anything that you have in mind about?
In general. By the way, we also mentioned before the proof that there is a zero-knowledge proof for Sudoku, which I may do. It may be deleted later on. It's going to be the last item.
Okay.
So, first of all, computer science, theoretical computer science and mathematics. It's a new kind of mathematics. And its penetration and place into classical mathematics and place into current versions of classical mathematics has not yet fully occurred. But I'm sure that because of the enormous importance of computer science, this will happen, and very respectable mathematicians will build a career upon discovering new facts, theorems, counterexamples in computer science and theory of computing. Now, some people may not like me in view of what I'm going to say next. Roughly speaking, in the second half of the 20th century, there were three great revolutions in science. And these are atomic energy, started earlier, of course, which maybe we can summarize by E=mc². The double helix, DNA, and all the consequences, and computing and computer science, starting with Turing and von Neumann's work. Now, let us hop ahead to 2015. Of these
2050.
even, okay, no, would say 2050, but 2025. So, atomic energy, well, it's true that in France 70% of the electrical energy is produced by atomic energy, but in France there live 70 million people. On Earth there are now maybe 6 billion people. Atomic energy didn't really change our lives. You don't, and I don't care whether my electric shaver is run by electricity produced by natural gas or by atomic energy. Now, despite the wonderful scientific breakthroughs in molecular biology, as best as I know, there isn't as yet a single disease which has been cured by genetic engineering. There are new drugs maybe which are
Techniques.
techniques composed by using DNA, but it didn't really change our lives that much. However, if you look at computing and you look at where it went since I went to Princeton to study computing and what became helping also to create what became computer science, completely changed our lives. The workplace, social interaction,
Information, knowledge,
communication,
security.
and we don't know what the future, even in the coming 10 years, holds. So computing turned out to be the biggest winner, way above physics, and as of now, even biology, in terms of its impact on our real life.
I think this is a wonderful place to stop. We can do the Sudoku some other times, but Michael has a wonderfully easy proof, zero knowledge proof of Sudoku. I'd like to thank you for this interview. Especially I want to add again, since you've had some health issues, might have been sensed by some of the viewers, a little difficulty here and there, but you did a tremendous job here, and I'd like to wish you health and more years of productivity. We need you for a long time with us.
Thank you
Be
very
well.
much.
Thank you.
Thank you for being such a wonderful guide and in the interview.
I didn't have to. I didn't have to do much. You had it all laid out. Thank you.
Thank you.
Thank you, Michael.